This video is connected to the November 6th remote session where we're learning about raster. This will be a relatively short video to end it. It's sort of the last tool I want to demonstrate, the last basic tool. And then next week we'll pivot into sort of the more complex and practical applications of raster. But I'm going to demo a tool called Euclidean Distance. So if you want to follow, just bring in the Euclidean example. And I'm going to demo it, one, because it's a useful tool that's sort of the approximation of buffer. It's what lets you show distance. But it's also useful and instructive for me to demonstrate the concept of extents and cell size. We know these already. We've been talking about how the rasters are like grid cells or like a piece of graph paper, and every cell is the same size. But we need a way to determine that when we create new grids, we want to make sure that every grid is the exact same size, the same extent, and the same cell size, so that it lines up perfectly and we can analyze it better. And I'm going to show you what I mean by that by running the Euclidean distance in sort of two fashions. So come on over here to Tools, Spatial Analyst Distance. Oh, that's fascinating. So legacy tools, look at that. Sometimes calculates the distance for each cell to its sources, allowing for straight line. Oh, so this is cool. So I guess now they've combined all of the different distance types into sort of one. That's very interesting. But legacy is, I think, what we're going to do. We want to go to the legacy tool just called Euclidean Distance, which is the quicker distance, sort of as the crow flies, like buffer. And so what does it want? It wants either sort of a raster or a feature source. So we'll drag in the points. Notice it's going to ask me what cell size I want. And if I just let it be, it would default to one that's weird and definitely larger than the 100 cell size I have for elevation or land cover. And it might make sense, in fact it does make sense, to want to keep the cell sizes the same so that things line up. So I'll change it to 100, which I know is what I want. Raster or barrier data, there's no barrier. Cell size, maximum distance, if you wanted it to cut off after a certain point. But for right now, let's just keep it as is. And it'll run it. And I want you to think about what you see, both in terms of the individual picture and then more importantly, where it stops. Where does it stop measuring distance? Notice there are 5 points here. And it comes out looking sort of crazy, right? Values between 0 and 5,800. And really what it's measuring is the distance to any one of these points. Right? So if I'm here, I'm 5,000 feet away from a point. The closer I get, right, I'm 1,900. When I'm at this line, I'm 41,000 feet. But if I keep going, right, I get closer to another one and I'm 39. So it's like buffer, except instead of just being one uniform distance, it literally has every cell tell you exactly how far away it is from a given area. Now what's interesting about this is notice that if you don't tell it otherwise, anytime it measures distance, it only makes itself as large as the points or the sort of extent of what you're measuring. And so since this was the southernmost point, that's where it stopped to the south. This is the westernmost, so it stopped to the west. This is the northern. This is the east. So technically what we need to do here is if we ever wanted to like add this or combine it with elevation, it's not going to work, right? I mean, they don't add up perfectly. It'd be like two misaligned pieces of graph paper, one that you see right on and one that is a bit more at an angle. And that's not going to be able to give us the sort of values or the analytics that we would want. So I'm introducing this to let you know that you can actually control under environments, either globally for every tool up here, or individually in each tool, the extent and the cell size. You can come in and say, hey, you're going to be the same size as land cover. And not only that, but your cell size is also going to be the same as land cover. And then what will come out will actually be a grid that is the same size. And so if I run it, I now have a more complete area that stretches out to the same cell size or the same extent as elevation. Now, a couple of you may see this for the first time and say, wait a minute, this isn't the same size as elevation. Look, elevation has a very different shape, but I want to show you something interesting. Look how the extent points, the northern, eastern, and southern points are all the same. See, the truth is, even though it looks like there's no value here for land cover, there is in fact a value, and if I click there, it's going to say no data. And that's a neat concept, is that anytime you have something with no data, no piece of information, right? There was nothing to digitize here. All I had to digitize was the land cover. It takes on this thing called no data. And no data literally means exactly what you think it means. There's just no information there. It's just filler. But these are actually the same exact size. They'd have the same number of pixels, and they have the same cell sizes, so they could be added and evaluated exactly together. So that's the basics of raster in these 4 videos. And then next week we'll dive a little bit more deeply into some practical applications, how we generate topographical surfaces, and how we calculate density.